All right, today we are going to look at more angle relationships in polygons. So I'm calling this the part 2. So we're starting off by looking at the sum of the exterior angles in any polygon. So we can make an exterior angle by extending a side of a polygon. So this right here is an exterior angle, and we can see that it forms a linear pair with the interior angle. So I'm going to go ahead and I'm going to fill in all of the missing exterior angles in this first problem here, this first example, because I want to show you how we get to the sum of the exterior angles in any polygon. Doesn't matter the number of sides. So here, if this interior angle is 40, the exterior angle would be 140. It's its supplement. If the interior angle here is 72, its exterior angle would be 108. That's its supplement. If the interior angle is 68, the exterior angle would be 112. It is its supplement. Okay, so now that I have those 3 exterior angles marked, if I add them up, it gets me to 360 degrees. All right, the next one that I've drawn is actually a rectangle, and I've marked all of the interior angles as 90 degrees. So all of the exterior angles would also have to be 90 degrees. And if I add all of those up, I am back to 360. Let's try one more figure. So here, if we look at this figure, I see a hexagon. So I have all of the interior angles marked as 120. So all of the exterior angles have to be 60. Okay, and if I add up all of those exterior angles, all of the 6 60-degree angles, I am back to 360. So one thing that we should notice that is staying constant is that no matter how many sides our figure has, this one had 3, here 4, this one had 6, we're seeing that the exterior angles all sum to 360 degrees. Now let me show you why. So if I look here at the rectangle, for example, let's say that I put a little dot here that I picture that is the center of the figure. I want you to picture all of these sides as walls that are converging, that are closing in on that point. And what's going to end up happening, we draw that point right here, once all of these sides collapse into that one point, we have these segments that remain with these angle measures. So picture all of those exterior angles coming together. I can see it making that full swoop, that full revolution, right? 360 degrees right there. Okay, let's say I look at it for the hexagon example. So I picture here's my center. I picture all of these sides closing in, converging at that point. Right, and I'd have a figure that looks like this, with all of these 60 degrees wrapping around that one point, which we know is 360 degrees. Okay, so just 2 ways to look at it. So I can see that the sum of the exterior angles for any polygon will always stay constant at 360. Doesn't matter the number of sides. Okay, so let me say that back one more time. The sum of the exterior angles for any polygon always going to be 360 degrees. Okay, down below, I'm saying, well, what if we're looking at an exterior angle relationship for a regular polygon, and I want to know just one of them? So in my model here, right, I'm giving you a regular pentagon. So since it's regular, we know that that means that all of the sides are congruent. I can show that with tick marks. And all of the interior angles, they are congruent too. And if all of those interior angles are congruent, so are the exterior angles. So if I want to find one individual exterior angle measure, like this one right here, I need to find the sum of all of the exterior angles and divide it by n. N would be my number of sides. It would also be my number of exterior angles. So I'm really taking 360 and splitting it n ways. Pretty easy calculation. All right, so again, the sum of all of the exterior angles in any polygon, that's going to always be 360. If I want one individual exterior angle for a regular polygon, it has to be regular because that means that all of the sides and angles are the same. They're all congruent, right? I take the sum, 360, and I split it n ways. So that would get me this measure right here, right? The exterior angle. All right, let me slide up. Example 1. Find each of the following for a regular dodecagon. So regular implies that all sides, all angles are the same. Dodecagon, we got 12 sides. Okay, so first I want the sum of the interior angles. So the sum of the interior angles, we did this previously. We know that this is n minus 2 times 180. We know that that formula is derived by picking one vertex, connecting all of the diagonals, and finding the amount of triangular regions. So the amount of triangular regions is the n minus 2 part, and 180 represents the sum of the interior angles for any triangle. So we're looking at number of triangular regions and then multiplied by 180. So I'm going to plug in a 12 right here for n. 12 minus 2 times 180, or 10 times 180, gets me 1,800. So that would be the sum of all of these interior angles. And if it's regular, they are all the same. All right, let me label one of the interior angles. So here would be an example of one of the 12 interior angles. And then if I extend this side right here, I could extend any of them. That's going to produce for me an exterior angle. So we see that together they form a linear pair. They are supplementary. And I could have done that with any interior angle. So I could have picked this one, extended this side, and drawn in an exterior angle, for example. So if I want one individual interior angle, I know that all of them together sum to 1,800, and I need to split it 12 ways because I have 12 congruent interior angles. So my formula is the sum, again, n minus 2 times 180, but I have to divide it by n. So I already know my sum, right? I calculated that previously, 1,800, and I split it 12 ways, and I get 150. So 150 degrees. Okay, sum of the exterior angles, well, that's the easiest calculation we'll have all day because we don't have to do much. It's always 360. It is always constant, regardless of the number of sides, right? That is going to stay put at 360. Okay, if I want one individual exterior angle, right, my figure's regular, so they're all the same, then I'm taking the sum, right, always 360 for exterior angles, and I'm splitting it n ways. So 360 divided by 12 will get me 30 degrees. Okay, I want to point one thing out while I'm here. So remember what I showed you in the picture. Here I have an interior angle, here I have an exterior angle. I can see that together they form a linear pair. They have to be supplements, right? They are supplementary angles. So when I go back here, I'm just going to remind you then that these measures have to add to 180. So it's just a way of double checking that we did this calculation correctly. So let me just write that. So supplementary if it's a regular polygon. Okay, and then lastly, let me slide that over. Lastly, I want a central angle. So a central angle, we've seen it before, it's been a while. So a central angle, let me find the center of my figure right here. Okay, so about right there. So if I look at two vertices that are right next to each other, so consecutive vertices would be like here and here. So if I connect and I make an angle with the vertex at the center, like so, that is one of 12 central angles because it's a dodecagon. It's a regular dodecagon. So I could do that same process with each of these vertices as it wraps around, and I would see that I have 12 congruent central angles. So right here is my central angle. When we were talking about symmetry, and we were talking about rotational symmetry specifically, that was the degree measure that we were calculating when we were saying that a figure rotated to map onto itself. So that is what we're calculating here. So we know that all the way around is 360. So I need to take 360 and split it n ways. So it's the same exact calculation as an exterior angle, but it does represent a different part of the figure. So obviously, we know it's going to be 360 divided by 12, just like exterior angle. And again, we'll get the same measure of 30 degrees. All right, next up. The sum of the measures of the interior angles of a convex polygon is 4,140. Classify the polygon by the number of sides. Okay, so we should note that the sum of the interior angles is n minus 2 times 180. We're given the sum, so 4,140 equals n minus 2 times 180. And then from here, it's really just an algebra problem. We're trying to solve for n. N is our number of sides. It would also be the same as the number of angles, but we're focusing on sides. So from here, I want to get the n by itself. So I would divide away the 180. So I have 23 equals n minus 2. Okay, so now I need n by itself. I'm going to add 2 to each side, and I get 25. So my figure, my polygon, has 25 sides. Okay, all right, let's look at the next page. Here I have kind of some mixed practice of interior and exterior angles. Okay, so find the number of sides of a regular polygon if you know an interior angle has a measure of 160 degrees. Okay, so let me lay out that formula. I know that that is n minus 2 times 180, okay, divided by n is equal to 160. Okay, so now again, it's an algebra problem. I have to solve for n. So I like to clear my fraction first. So I'm going to multiply each side by n, which goes to 1 and 1 right here. So now I have n minus 2 times 180 equals 160n. So I'm trying to get n all by itself. So I need to first just distribute that 180 and then pull my n's to the same side. So I'm going to distribute here. I get 180n minus 360 equals 160n. Okay, then from here I'm going to take away 180n. I get negative 360 equals negative 20n. Divide each side by negative 20. And I get 18. So my figure would have 18 sides. Okay, for example 4, find the number of sides of a regular polygon if you know an exterior angle has a measure of 15 degrees. Okay, so I know then that 360 divided by n equals 15. And now I'm solving for n. So again, I like to clear my fraction. I'm going to multiply each side by n. So again, 1 to 1 here. So I have 360 equals 15n. And I can divide away the 15. And I get that n is 24. So my figure has 24 sides. All right, something fun to point out is this is clearly the easier method of the two. So if I go back over to here, if I know an interior angle is 160, I actually know an exterior angle would be 20 degrees, right? Because it would be its supplement. So if I know that, I could actually work through this problem here, example 3, in the same way I did example 4. I just have to see that connection. So if I give you the interior angle of a regular polygon, you actually know the exterior angle too. They are supplements when the figure is regular. All right, next up. Here in this problem, I'm giving you all exterior angles. So I know that the sum of the exterior angles has to be 360. I know that this notation here means right angles, so 90 degrees. All right, so it looks like I have two x's. And if I add 75, 90, and 58, I get 223. All equal to 360. The sum of the exterior angles for any polygon, regular or not, right, is always 360 degrees. So now I'm going to take away the 223. So 2x equals 137. And then I need to divide each side by 2. So I'm going to get that x is 68 and a half. So 68 and a half degrees. All right, in B, I have a lot going on. I have a bunch of lines with transversals. I don't have any parallel notation, so I need to figure out how to connect my dots. So I would probably build off of any linear pair or any vertical angle relationship first. I'm trying to get over to where x is. So right where that 120 is, I'd see that its linear pair is 60. Right where this 100 is, its vertical angle is 100. Okay, its linear pair would be 80. Right, so I'm just trying to make as many connections as possible so I can eventually get over to where x is. Okay, I can see that 130, its linear pair would be 50. If these add to 130, this angle would be 50 also. And then linear pair here would be 130. Okay, so now I'm seeing that I have, right here, I have a quadrilateral. Quadrilaterals have to add up to 360. So if I add up 60, 100, 130, I'm at 290. So what's missing would be 70. I could have also seen this larger triangle that has to add up to 180 and gotten there a different way. And then if this is 70, its supplement, because they form a linear pair, is 110. So x is 110 degrees. Okay, one other thing that I could notice, let me point this out to you because I don't think many people would see it. I'm going to draw this triangle right here. And right now I'm going to extend just some of the exterior angles, where this is 120, this is 130, and then this is the 110 that we just saw for x. So if you look at that, let me just make sure you can see it. So if you look at that, so again, what I've framed is this part. Let me show you with my colored pencils that you know I love. So here we go. So if I'm looking at that triangle, right, I've just extended here to see these exterior angles, and I can see that those add to 360 as well. So that's actually another way to approach it without working through these interior angles in this space over here. All right, next up, I'm asked to solve for the measure of angle 1. So I want this measure right here. I'm given a combination of interior and exterior angles, so I can choose which way to go. Right, I actually have options here. Let's say that I go through the interior angles. Well, I have to connect here the vertical angle, which would be 100. This linear pair would be 85 because they're supplementary. And then let's say that I labeled this angle x. So I need to solve for x, and then angle 1, right, would be the supplement of whatever I get for x. So here I see that this is a pentagon. So I know that 5 minus 2 times 180, 3 times 180 is 540. So the sum of those interior angles is going to be 540. So x plus 105, 85, 135, and 100 adds to 425, all equal to 540. Okay, take away 425 from both sides, and I get that x is 115. Okay, now that I have what x is, let me just mark that. Here's 115 degrees. Remember that angle 1 is the supplement of x. So angle 1 has to be 65 degrees. Okay, one last one that has a little bit more algebra involved. So here it looks like we're given all of the exterior angles. And I'm trying to get to angle 1. So I need to solve for x, figure out what this measure is, and then I need its supplement right here. So here, let's see, the only quadratic term that I have is x squared, so x to the second power. If I look at all of these linear terms, I have the 5x, 8x, 7x, 10x, and 13x. Those sum to 43 x's. And then the constants, I have 8, take away 5, I'm at 3, plus 6, I'm at 9, and then plus 1, I'm at 10. And then the sum of the exterior angles is always 360. Okay, so I see, okay, it's a quadratic equation. I gotta make sure it's equal to 0 before I can solve. So I'm going to take away that 360 from both sides. So x squared plus 43x minus 350 equals 0. Okay, so now I'm looking for two numbers that multiply to negative 350 that add to 43. And if you ever get stuck, make a list. So here's 350. Let's look at the pairs. 1 and 350, not it. 2 and 175, right? Still not it. Not divisible by 3 or 4. So if I go to 5, 5 would pair with 70. Nope, not there yet. 7 would pair with 50. And there we go. So if you follow this system right here for factoring, it just helps you get to the right answer quicker. So now I see that it's going to be x plus 50 and x minus 7 equals 0. So I have x could be negative 50, x could be positive 7. So if I tried that negative 50, let's say that I plugged it in here, for example, I would have a negative angle measure. And I know that that doesn't work. That's an extraneous solution. I was able to solve for it, but plugging it back in does not actually work. So if I plug in the 7, right here, 7 squared, I'm at 49, plus 1, and I'm at 50 degrees. Okay, so I know that 7 is the one that works, and then 1 is its supplement, so 130. Okay, so the measure of angle 1 is 130 degrees. All right, last problem. So here we know that ABCDE here, this is a pentagon, and it's regular, and so is HIJKL. So these are both regular pentagons, and then here is a regular hexagon. All right, so we are also told that angle ABK is congruent to LBK, and we want the measure of ABK. Okay, so let's just unpack that for a second. Regular pentagon, regular pentagon, regular hexagon. In this figure, we're told that ABK, so this angle, is congruent to LKB, this angle like so. And ultimately, this is the one that we want. We want this one right here, but we know that these are the same. All right, so let's build off of why are we told that we have a regular pentagon? Why are we told that we have a regular hexagon? Well, a pentagon, we know that the sum is 540. So if I split it 5 ways, then each individual interior angle is 108. So I have a 108 here, for example. Okay, I also have a 108 here, for example. Now, all of them are really 108. I'm just marking these because I know I'm trying to connect over here to get to this measure in the end. All right, the regular hexagon, the sum is 720. I have to split that 6 ways, so I get 120 for each of the interior angles for a regular hexagon. So that means that right here is 120, here is 120 also. Okay, again, all of these are 120. I'm just marking the ones that are going to help me make a connection. So now I see how I can get to these 2 angles here and here. I can see that they're actually congruent as well. So if I look at this one, right, this would be a full 360. So if I take 360 and I subtract 120 and 108, I get 132. And I would get the same thing over here as well, 132. Okay, so now I know that this is a quadrilateral, 4 sides, has to add to 360. So I'm going to take 360. I'm going to subtract the 132 and the other 132, so 264. Okay, that's going to get me 96. So I know that together these have to add to 96 degrees, right? It's the leftover 96 degrees, and I have to split it 2 ways. And that gets me 48 degrees. So these 2 measures here have to be 48 degrees. So the measure of ABK, the one that I ultimately wanted, is 48 degrees. All right, have a lovely rest of your day.